Hello all. Welcome back to Tungal online classes. In the previous class, we were discussing when a bar magnet placed in an uniform magnetic field, how it experiences torque and what is the condition for maximum torque and minimum torque, along with if the magnetic needle placed in an uniform magnetic field, how it experiences torque along with how it oscillates in a magnetic field with the time period t. And already we have seen that how much magnetic field required to oscillate the needle in an uniform magnetic field. That concept in the last class we have seen. Now in this session, let us take when a magnetic dipole placed in a uniform magnetic field or a bar magnet, or you can take a magnetic needle, no matter. When a magnetic dipole placed in a uniform magnetic field, what is magnetic energy associated with it? That concept we will see. Along with what is Gauss line magnetism, that concept we will see. So initially let us start magnetic energy of magnetic dipole. Magnetic energy or simply magnetic dipole or potential energy of magnetic dipole. Potential energy of magnetic dipole in an uniform magnetic field. In an uniform magnetic field. In an uniform magnetic field. This concept we will see in detail. Right. So here, initially we will take a magnetic needle or you can take a bar magnet. That magnetic needle or bar magnet placed in a uniform magnetic field. That we will see. So here. Now, shall I take a magnetic needle? I will take a magnetic needle like this. See here. This is the magnetic needle. Right. So this magnetic needle consists of what value? It consists of south pole. Right, it consists of north pole. Right thing. The line joining from north pole to south pole, this we are calling magnetic axis. Right, are you following? Now this magnetic needle placed in an uniform magnetic field. Right, how it is? See here. Now I would like to take uniform magnetic field lines. These are nothing but uniform magnetic field lines. Right thing. This is the uniform magnetic field lines. This uniform magnetic field lines, that value has B. This is the value B. Now, in presence of magnetic field B, the north pole experience force. How much force experience? North pole experience force, that force is equal to what value? Force is equal to small m into B. What is small m? Pole strength of the magnetic needle. Similarly, in presence of this magnetic field B, this south pole experience also force. In what direction? This also experience force how much? It is small m into B. So, in presence of magnetic field B, the north pole and south pole, they experience equal and opposite force. They experience equal and opposite force, so the torque is acting. How much a torque is acting? In the last class already we have seen. The torque experienced by the magnetic dipole can be given, that value is equal to m into b sin theta. M into b sin theta. What is m actually? M is nothing but magnetic dipole moment. That magnetic dipole moment can be traveled from where to where? It can travel from south pole to north pole. Shall I take this value? Capital M. And what is theta? Theta is angle made by magnetic field with the dipole moment, that is represented by theta. Right. What is B then? B nothing but strength of the magnetic field. Now due to this magnetic field, it experiences torque. Due to this torque, this magnetic dipole or magnetic needle, it tries to rotate along the direction of magnetic field. When this dipole tries to rotate along the direction of magnetic field, it rotates with an angle d theta. Consider, due to this torque, this dipole, how it rotates? This dipole tries to rotate along the direction of magnetic field. So that during rotation, it rotates with an angular displacement of what value? D theta. How it rotate? It rotates from some value, say theta 1 to theta 2. So that additional angular displacement equal to what value? D theta. We know that wherever torque is acting and angular displacement is there. For rotational motion, how to define work? For rotational motion, work done is equal to the cross product of torque and angular displacement. Here d theta represent angular displacement and tau represent torque. So that work is done by the dipole. How much work is done? Work done can be taken dw. What is dw? dw is equal to what value? So tau into d theta. Right? Now what is tau actually? Tau is equal to mb sin theta is available. Then how much work is done? Total work done can I shall I take? dw is equal to what value? dw is equal to how much? Tau. Tau is equal to how much? It is m into b sin theta. M into b sin theta into how much? D theta. Are you following? But due to this work and due to this torque, this magnetic dipole rotates from theta 1 to theta 2. Say it rotates from theta 1 to theta 2. When it rotates from theta 1 to theta 2, the net work done can be taken by taking integration. How to take the integration? Look at me. So I can take the integration of what value? dw. Integration from where to where? From theta 1 to what value? Theta 2. What value? This is m into b. M into b sin theta. Sin theta into how much? D theta. Right? This dipole rotates from theta 1 to theta 2 due to angular displacement d theta. Right. Then we know that here what are constant values? Shall I take one more step here? What are constant values? Here capital M. Capital M is the constant. Magnetic dipole moment. Capital B also constant. Strength of magnetic field. So constant value shall I take outside during integration? So that m into b keep it up saying. Right or wrong? From where to where? See here. From theta 1 to what value? Theta 2. Sine of how much? Sine of theta into d theta. Right. We know this is the form integration of dx and integration of dw. What is integration of dw? Integration of dw is equal to w. Right. See here. Integration of dw is equal to w. Capital M keep it up same. Capital B also keep it up same. What is integration of sine theta into d theta? Integration of sine theta into d theta is equal to minus of cos theta. So that how to take integration of this value? Integration of this value is equal to what value? Cos theta. From where to where? From theta 1 to what value? Theta 2. Right? Here minus sign is there. Shall I take it directly? One more step I will take. Total work done is equal to what value? Total work done is equal to m into b minus m into b. Take him outside. So cos theta. Cos theta how much? Cos theta 2 minus of what value? Cos theta 1. Right or wrong? Or if you multiply minus inside, then what it becomes? W is equal to how much? W is equal to m into b. M into b from where to where? From cos theta 1 to minus of what value? Cos theta 2. Right or wrong? Now students, when work is done on the dipole, this work is stored as magnetic potential energy of the dipole. When a dipole rotates from theta 1 to theta 2, how much work is done? This much work is done. W is equal to what value? M into b cos theta 1 minus of what value? Cos theta 2. This work is stored as potential energy. This work is stored as potential energy when the dipole rotates from perpendicular direction of magnetic field to equilibrium position. Then work is stored as potential energy. When work is stored as potential, that condition we will see. Initially, let us take a dipole placed in a magnetic field perpendicular to direction of magnetic field. Perpendicular mean, shall I take here? Look at me. Again I will take this nothing but magnetic needle that placed in a uniform magnetic field. Right or on this? This is nothing but magnetic dipole. So this consists of what value? South pole. What about this? This is the north pole. Right? North pole. Then what is the direction of magnetic field? This is nothing but direction of magnetic field. I can call this the direction of magnetic field. Right? Are you following? What value? This is B. Now magnetic dipole moment from where to actually it is nothing but magnetic axis line joining from north pole to south pole. What is direction of magnetic dipole moment from south pole to north pole? What value? That is capital MB. Right? Now this is the angle. What is angle? Angle between magnetic dipole moment and magnetic field. Here how much angle available? Theta is equal to how much? Theta is equal to 90. I mean initial theta how much? Initial theta 1 is equal to 90. When a dipole rotates from perpendicular direction of magnetic field to equilibrium position. Equilibrium position means angle between magnetic dipole moment and magnetic field must be same. Then this total work done is nothing but stored as potential energy. That potential energy we are calling magnetic potential energy of the dipole. I mean now condition is like this. Theta is equal to 90. When this dipole rotates from theta 1 is equal to 90 to theta 2 is equal to some value. Some value mean, shall I take here? Again I will take like this. See here, this is nothing but magnetic, this is nothing but magnetic field lines. Are you following this? So this is nothing but like this. If the dipole rotates from theta 1 is equal to 90 degree to theta 2 is equal to some value. Shall I take now? Now I will take. This is nothing but a magnetic dipole. So again it is south pole. What about this? This is the north pole. This is nothing but direction of magnetic dipole moment. Represent by what value? Capital M. Now this is somewhat angle. Theta T is equal to what value? Theta 2. When dipole rotates from theta 1 is equal to 90 degree to theta is equal to theta 2. Theta 2 whatever value. It may be 60 degree, it may be 30 degree, it may be 0 degree. So when magnetic dipole rotates from theta 1 is equal to 90 degree to theta 2 is equal to theta, then this total work done is nothing but stored as magnetic potential energy. I mean condition must be directly, shall I take? The total work done stored as potential energy for this condition must be equal to theta 1 is equal to 90 degree and theta 2 is equal to what value? Theta. Right? Now, shall I take here? If the case, then this total work done is nothing but what value? Total work done is nothing but potential energy of the magnetic dipole. Now I will take. See here, this is nothing but potential energy. Potential energy can be represented by U. So M into B keep it up same. M into B keep it up same. So theta 1 is equal to what value? 90 and theta 2 is equal to what value? Theta. Right? Cos 90 that is 0. Wherever cos 90 is 0, then what is potential energy? Potential energy is equal to how much? M into B cos theta. Right? So or in vector form how to write? In vector form can write directly what value? This is M dot B. This what value? This we are calling potential energy of the magnetic dipole when it is placed in an uniform magnetic field lines. Are you following me? Then let us take what is condition for stable equilibrium, condition for unstable equilibrium and condition for neutral equilibrium. I mean whenever dipole placed in a uniform magnetic field, it exists this much of potential energy. Now we will see the special cases. In what cases the dipole has maximum potential energy, minimum potential energy, and what conditions we are calling those. See here. Now initially you can take when a dipole aligns along direction of magnetic field. Direction of magnetic field means, shall I take here? So I can take this nothing but a magnetic needle. This is the magnetic needle I can take. Are you following this? So this we are calling what? This is nothing but south pole. What about this? This is the north pole. This is nothing but magnetic dipole moment from where to where? From south pole to north pole. Right? Now in the dipole rotates from theta 1 is equal to 90 degree to theta 2 is equal to 0 degree. Theta 2 is equal to 0 degree. 0 degree mean, shall I take here? So I will take this nothing but uniform magnetic field lines. Are you following this? This is nothing but B. Now what is angle between B and M? Angle between B and M is equal to what value? 0 degree. Right or wrong? If theta is equal to degree, cos 0 is 1. Cos 0 1 mean what value? Now can take this what value? This value is equal to M into B. Then this value is said to be minimum energy. When dipole has minimum energy, then that condition is said to be stable equilibrium. I mean, when dipole rotates from theta 1 is equal to 90 degree to theta 2 is equal to 0 degree, then this much energy must be exist. This energy has minimum energy and this minimum energy condition must be stable equilibrium. When magnetic dipole has minimum energy, then you can call the magnetic dipole is said to be in stable equilibrium. right? So this we are calling, this is nothing but minimum energy, this we are calling minimum energy, and this condition is called as a stable equilibrium, because it has minimum energy. It has minimum energy. Are you following this? Now let us take, when a dipole rotates from theta 1 is equal to 90 degree to theta 2 is equal to 180 degree. 180 means, shall I take here? Same condition I will take. Look at me. Second condition, how to take here? Simply I will take. See here. So this is nothing but magnetic field lines. Shall I take here? This is nothing but magnetic field lines. Are you following? This I can call south pole. What about this? This is the north pole. Now in this case, what is direction of magnetic field lines? From south pole to north pole, represent by what value? M, and magnetic field is B. Now what is direction of magnetic field and magnetic dipole? Both are in what direction? Opposite in direction. Then how much angle available? Theta is equal to what value? 180. Right? If theta is equal to 180 degree, theta is equal to 180, cos 180 minus 1, minus into minus, that becomes plus. Then what is potential energy? Potential energy, U is equal to what value? U is equal to plus M into B. It has maximum energy. I mean, when dipole rotates from theta 1 is equal to 90 degree to theta 2 is equal to 180 degree, it has maximum energy. The maximum energy condition we are calling unstable equilibrium. Unstable equilibrium ಅಂತ ಹೇಳ್ತೀವಿ. See here, this condition I can call unstable equilibrium. Unstable equilibrium. Unstable equilibrium. The second condition. Then third condition, when dipole exactly perpendicular to direction of magnetic field. Perpendicular mean, so again I can take, shall I take like this? Perpendicular direction mean, how we will see? Look at me. This is nothing but magnetic dipole or magnetic needle placed in a uniform magnetic field. I can call this is south pole. What about this north pole? And what is direction of magnetic dipole mean? From south pole to north pole. Shall I take this? Like this. So what value it is B? What angle available here? 90 degree available. Wherever cos 90 is 0, wherever cos 90 is 0, then U is equal to what value? 0. Because cos 90 is 0, 0 into this value is 0, then what is potential energy? Potential energy must be 0. I mean, when bar magnet aligns along direction of magnetic field, it has minimum energy and stable state. When dipole rotates anti-parallel to direction of magnetic field, it has maximum energy and unstable state. But whenever dipole is perpendicular to uniform magnetic field lines, it has maximum torque, but energy must be 0. That energy is 0, then that dipole is said to be in neutral state. See here, this dipole, it has 0 energy. Wherever 0 energy, then what you can call? This state is said to be in neutral state. Neutral state means, this is the position where it has a 0 potential energy. When magnetic dipole aligns perpendicular to direction of magnetic field, it experiences maximum torque, right? But it exists at 0 energy. That point we are calling 0 potential energy point. This point I can call, this state I can call 0 energy potential energy. 0 point potential energy of a magnetic dipole. So this is potential energy of magnetic dipole in an uniform magnetic field. Now let us see the next concept. Concept is Gauss law in magnetism. That concept tells in detail. See here. Our next concept is Gauss law in magnetism. That concept we'll see in detail. Right. Concept is Gauss law in magnetism. Students, already we have seen that Gauss law in electrostatics. In electrostatics, already we have seen electric flux. What is electric flux there? Number of electric field lines passes through surface, that we are calling electric field lines, or the scalar product of electric field and area vector, that we are calling electric flux. In electrostatics, we have seen the Gauss law. What is Gauss law there? The total electric flux through closed surface is equal to 1 by epsilon naught times total charges enclosed by closed surface. And on that basis, we have seen few applications on the Gauss law. But the Gauss law in electrostatics is different from Gauss law in magnetism. To understand the concept of Gauss law in magnetism, we should know the term magnetic flux, right? And we should know the terms magnetic field lines and few property of the magnetic field lines. So before that, let us see what is magnetic flux. How to say the magnetic flux actually? So I can take magnetic flux quantity. How to take magnetic flux? Right? Look at me. To understand concept of magnetic flux, simply already we have explained in moving charges and magnetism. So what is meaning of magnetic flux? Simply I will explain now. See here, I can take a closed surface. So this is nothing but closed surface I will take. Closed surface means you can take Gaussian surface, right? So on this closed surface, if you take very small area, and from that area if we draw a perpendicular line, that becomes area vector. For example, now shall I take actually? So if I take very small area and if we draw a perpendicular line, this becomes area vector. Are you following? Or you can take any point, you can take. Any point mean you can take here also. If I take very small vector, so if we draw a perpendicular line, this becomes area vector. What is meaning of this? Whatever line with arrow mark, this represent area of the surface. Area of the surface. The line with arrow mark, length of this arrow mark represent area of the surface. This we are calling area vector. Now through this closed surface, let us take number of magnetic field lines or passes. How it is? See here. Now I can take this nothing but magnetic field lines passes through the surface. Are you following? Like this I can take. So what value? This value is equal to what value? B. Right? What is magnetic field lines? Magnetic field lines is nothing but the number of magnetic field lines passes through surface normally. I mean, how many magnetic field lines are passes in a given surface perpendicular to it, that concept we are calling magnetic flux. And mathematically, how to say? Mathematically, the magnetic flux is equal to scalar product of magnetic field and area vector. Scalar product of magnetic field mean what value? It is B into ds cos theta. This we are calling magnetic flux quantity. Are you following me? Magnetic flux mean what? The number of magnetic field lines passes through surface perpendicular to it. To this surface, these are the field lines they can passes. This number of field lines can pass, that we are calling magnetic flux. Right? And the quantity magnetic flux already we have seen, it is a scalar quantity. Students, to understand the concept of Gauss law in magnetism, we should know some property of the magnetic field lines. What is the property of magnetic field lines? Simply magnetic field lines can travel from north pole to south pole outside the magnet, and south pole to travels inside the magnet. How they travel? From north pole to south pole outside the magnet, and they travels from south pole to north pole inside the magnet. Right? See here, I mean, these magnetic field lines can travel from north pole to south pole. They can travel like this. Right? And I will take a bar magnet. For that bar magnet, simply how to take the magnetic field lines already we know. See here. Now I can take this nothing but bar magnet. This is the bar magnet. Right? Simply I will take. So this is nothing but north pole I can take. So this is south pole. Magnetic field lines, how they travels? They travels from north pole to south pole outside the magnet, and south pole to north pole inside the magnet. Right then. How they will travel? Simply they will travel like this. North pole to south pole outside the magnet, and south pole to north pole inside the magnet. Like this. Like this they will travel. Like this they will travel. Right or wrong? Like this I will travel. Like this they will travel. Are you following this? Right? Every magnet consists of equal and opposite pole strength. Every magnet, either whatever you can take bar magnet, you can take magnet needle, you can take U-shaped magnet, or you take natural magnet also. How to confirm? When a bar magnet freely suspend, it aligns in north-south direction. So from that you can confirm every magnet consists of a north pole and south pole. Right? See here. This magnet consists of equal and opposite pole strength. This consists of pole strength M value and this also consists of pole strength M value. Equal and opposite pole strength are there. My concept is Gauss line magnetism. In Gauss line magnetism, the concept how we will take? In a uniform magnetic field line or in a non-uniform magnetic field line, I will take a closed surface. So shall I take here? These are nothing but number of magnetic field lines travel. Are you following? Like these are nothing but number of magnetic field lines. In this magnetic field lines, I will take any imaginary closed surface, or I will take real closed surface. See here. In this magnetic field line, shall I take? I will take this nothing but a closed surface. Right or wrong? This is nothing but closed surface. Or in this one, in this uniform magnetic field lines or non-uniform magnetic field lines, I can take this nothing but a closed surface. Right? We know the concept of magnetic flux. Concept of magnetic flux indicates that magnetic field lines number of magnetic field lines passes through surface. Look at this closed surface. In this closed surface, how many magnetic field lines are entered? How many magnetic field lines are entered? That much magnetic field lines are leaving. I mean, number of magnetic field lines entering must be equal to number of magnetic field lines are leaving. Right? In this case also, number of magnetic field lines are entered must be equal to what value? Number of magnetic field lines are leaving. Or similarly, you can take here also one closed surface. Look at me here. This is nothing but one closed surface I can take. One closed surface, or I can take here also one closed surface. Are you following this? In this closed surface, how many magnetic field lines are entered? That much magnetic field lines are leaving. Here also, how many magnetic field lines are entered? That much magnetic field lines are leaving. What is magnetic flux? Number of magnetic field lines are entered. Wherever magnetic field lines are entered, then magnetic flux exists. See here. If one field is entered, second field is leaving, or number of two fields are entered, two fields are leaving. Here also, two fields are entered, two fields are leaving. Number of magnetic field lines are entered must be equal to number of magnetic field lines are leaving. So that the Gauss line magnetism, what it says? Gauss line magnetism says that the total magnetic flux through any closed surface is zero. What I am saying? Total magnetic flux through any closed surface is zero, because number of magnetic field lines are enter must be equal to number of magnetic field lines are leaving. So statement of Gauss line magnetism, what it says? The net magnetic flux through any closed surface, the net magnetic flux through any closed surface, any closed surface must be zero. So this we are calling Gauss line magnetism. I mean, the net magnetic flux through any closed surface, is zero, or can it simply the total magnetic flux through any closed surface must be zero. Why it is zero? Zero mean how many magnetic field lines are enter, that much magnetic field lines are leaving. Look at this surface also. It is nothing but closed surface. In this closed surface, 3 magnetic field lines are enter and 3 magnetic field lines are leaving. Entering is equal to leaving. If number of magnetic field lines are enter equal to number of magnetic field lines are leaving, then total magnetic flux through any closed surface must be 0. Then what is physical significance of Gauss line magnetism? The physical significance is the magnetic monopole does not exist, because these magnetic field lines can travel from north pole to south pole. To exist a magnet, there must be a north pole, there must be a south pole, so that magnetic field lines can travel from north pole to south pole. So that this indicates that if entering is equal to leaving, mean magnetic field lines are leaving from north pole and magnetic field lines are enter into the south pole. Entering from north pole, leaving from north pole and entering to the south pole. This indicates that a magnetic pole monopole does not exist. Wherever magnet or wherever bar magnet, there must be a north pole and there must be a south pole, so that magnetic field lines are enter and magnetic field lines are leaving. Simply, the physical significance of Gauss line magnetism that magnetic monopole does not exist. See here, this indicates that this Gauss line magnetism indicates that magnetic monopole does not exist. Magnetic monopole doesn't exist. Wherever magnet, there must be north pole, there must be a south pole. Due to that, magnetic field lines are leaving from north pole and entering into the south pole. But here we have seen that Gauss law in electrostatics. In Gauss law in electrostatics, total electric flux through any closed surface must be equal to 1 by epsilon naught times total charge assigned closed by closed surface. In Gauss law in electrostatics, when electric flux is 0, already we have seen that. See here, shall I take here? I can take this nothing but closed surface or imaginary closed surface. This we are calling Gaussian surface. In the Gaussian surface, let us take number of electric field lines or passes. So represent by what value? E. And in this closed surface, how many charges are there? Let us take number of charges are there. Look at me here. Number of charges are there. Right. According to Gauss law, what you can take? The total electric flux means E into ds equal to what value? So 1 by epsilon naught times total charge assigned closed by closed surface. That equal to E into ds is equal to what value? Q by epsilon naught. Right. This is nothing but electric flux. Gauss law in electrostatics, electric flux is 0 only for two conditions. Condition is, in the Gaussian surface, it must contain dozen charges. I mean, in this Gaussian surface, if total charge is 0, if the case Q is equal to 0, wherever Q is equal to 0 by any value 0, then 0 is equal to what value? This 0. So flux is equal to what value? Flux is equal to 0 if the condition Q is equal to 0. In Gauss law in electrostatics, wherever charge 0, then only electric flux is 0. One more condition is there. If the Gaussian surface contain equal and opposite charges, shall I take again? So look at me. Again, this is nothing but a Gaussian surface. If it contain plus charge and if it contain minus charge. For plus charge, electric field lines are radially outward. For negative charge, electric field lines are radially inward. Number of electric field lines are enter must be equal to number of electric field lines are leaving. This is entering, this is what value? Leaving. Here what is total charge? Total charge Q is equal to what value? Q is equal to plus Q and minus Q. Total charge is equal to what value? 0. If total charge is 0, then what can take? So phi is equal to what value? Phi is equal to Q divided by epsilon naught. Q 0. I mean dipole is present. Wherever dipole mean equal and opposite charges separated by small distance. Wherever dipole present, total charge 0. Wherever total charge 0, then what is flux? Flux must be 0. So that in Gauss law in electrostatics, we can confirm that wherever charge is 0 in a Gaussian surface or dipole is present in it, total electric flux is 0. But in Gauss law in magnetism, what you can take? If you take any imaginary closed surface, in that closed surface, how many magnetic field lines are enter, that much magnetic field lines are leaving. So that net magnetic flux through any closed surface must be 0. This we are calling Gauss law in magnetism. Simply Gauss law in magnetism indicates the magnetic monopole does not exist wherever magnet, it must be North Pole and South Pole. Students, after this let us see the one more phenomena, terrestrial magnetism in detail. The terrestrial magnetism concept we will see in the next class. Thank you.